Yeah, thank you very much. So, hi everyone, my name is Maxime Popoff. I'm a PhD student inside the MWOT team, and today I will talk about high-level programming FPGA with FAUST. So the MWOT team is a team inside the City Lab, which is in this building. It's a collaboration between INRIA, INSA Lyon, and GRAM CNCM. It is the Sifara project, basically, that Loïc told you earlier. So what is the Sifara project? Well, the idea is to make sound on FPGAs. So an FPGA is a very powerful embedded platform. So I will explain later what it is exactly, but just admit for now that is a very high performances platform that you can program. So we want to use those platforms, but we want to make their use easy for the audio community. So we want to use a high-level programming language, like FAUST, for example, which is very used in the audio community, to make the programming of audio DSP on FPGA easy. So this is the idea behind Sifara. Sifara is it takes the shape of a command line in Linux. It's a compiler. And so, yeah, here it is. So what is an FPGA exactly? So it stands for Field Programmable Gate Array. So the field programmable is because basically it's reprogrammable. It can be obvious, but it's not because it's hardware. So it's the only way to reprogram hardware is to use an FPGA. It contains a lot of little logical block, very simple function that you're going to use to program them. So you have a lot of them, you wire them in the right way, and you can do your function, right? And so, yeah, array because there is that billion of them on one FPGA. So, yeah, an FPGA is really a little chip. It's like 1 centimeter per 1 centimeter of silicon, and you have everything you need on it. So, what exactly are these logic gate and this little block? Well, it's some small logic block that you have. I'm going to explain later what's inside it. So you have to compose with them to do the function that you want to do, right? So you have a lot of them. You choose them and you configure them the way you want. For example, those one. And you will connect them the way you want. And then you have your function, your hardware function. Those little blocks, it's called configurable logic block, CLB. So it's made of one lookup table and one register. So it's allow you to do any logical function n-to-1. If you want to do a logical gate or a NOT gate or OR gate, you can do it. You can do a multiplexer, you can do a custom state machine. Every logical block can do that, and you have billion of them. So if you connect them the right way, you can do any logical function that you want. So the idea is that there is a register. So you have the idea of clocking thing. This is not just you put something in the input and you have output. You can really process serial data, you can process parallel data, you can do a lot of things with them. So yeah, you can really do any hardware function that you want. You have other blocks inside the chip, so you have memory blocks, it's called BRAM. It's a very fast memory, but there are few of them. You have some DSP blocks, it's specialized block for mathematical function, and you have some clocking blocks, so you can do some PLL and something like that. So this is the idea behind the FPGA. You have your logical little block, you wire them the right way, you configure them the right way, and you can do any function that you want. Here you have, for example, two different functions. They are very simple on this one. So it's configurable hardware, all right? You don't by hand wire every logical gate. It will be a very long process. So you can program them using a language. It's called a hardware description language. It's a special programmation language that we will see later. But yeah, you can program them using a language. You don't really program them because there is no software. So we talk about configuration. You configure them, you don't program them, but it's kind of the same. So yeah, what's the difference with a CPU? Because you probably know how a CPU works. So on a CPU, if you want to do any instruction, let's say you want to do an addition, The CPU will fetch the instruction, decode it, take the arithmetic and logical unit to make the computation, store the instruction. On an FPGA, you really have the hardware function that is code, right? So it's very fast. You put some input, you have the output. It's physically here. So here, for example, with an addition, you take one logic block, you do a XOR gate with it, you take another logic block, you do an AND gate with it, you connect them the right way, and you have your adder, okay? So the only thing that limits the thing you can do on an FPGA is the number of logic blocks, basically. If you, as long as your function can fit in the number of logic blocks that you have, you can do any function. On a CPU, you will be limited by the frequency of your CPU and by the number of core. So this is really not the same needs. So what can we do with an FPGA? Well, basically, you can easily parallelize things. If you have your function, you can just duplicate it, and as long as you have enough resources, again, you can duplicate it how many times you want. So this is pretty nice for parallel data processing. You also have a lot of input and outputs on an FPGA, like 100 of the one I work with. So you can do a lot of parallel data processing. So for audio, for example, you can imagine multi-channel that can be handled easily. On a CPU, if you want to really do some function exactly parallelize them, you have to do one function per core, so you will be limited to 4, 8 maybe. So you cannot do that really. On FPGA, you can really parallelize 100 functions if you want. You have another thing, pretty nice. You can pipeline things. Okay, so if you want to process, let's say, some serial data, for example, some sample of audio, for 3 functions. So you can imagine that every function is a block, a physical electrical circuit in one block. On a CPU, everything going to be sequentialized. So you do every function, you have your data 1 goes out, the next data goes in, 3 function, data goes out. And you can pipeline things on a FPGA. So you put the first data on the first function, and when the first function is done, you can instantly put the second data. You don't have to wait for the first data to be fully processed. You can just put the second one as long as the first block is available. Okay, so you can pipeline things, and it's really increase the throughput. As you can see on the first example, it takes like 9 time slots to process 3 data, where it takes only 5 when you pipeline. So it does not reduce the latency. In both cases, one data takes 3 time slots to be processed, but it increases the throughput. Okay, so this is an FPGA basically. This is why they are pretty interesting for real-time audio processing. You can have high throughput, very low latency. I will talk about that later. You can have a high sampling rate, like more than 20 megahertz, for example. You can have a very high number of input and outputs, and you can do some parallel data processing easily. So they are already used for audio processing, not a lot, but they are already used. You have some example here. So for example, for the Innovation Summit keyboard, they are used for very specific function. So it's only for a very high audio sampling digital oscillator here. But they're already used, they're already interesting. But not a lot. Why? Because they are very, very difficult to program and to use. So I have a little example here. It's a little bit biased, I'm going to explain. If you want to do an addition on C, you will just have this line. On an FPGA, it's a little bit more complicated. First, you have to declare everything, every interface. Here, if I have 2 signal input, 2 signal output, I have to declare everything, and you have to do your computation. So here, it was just to show you that you can basically say that you want an XOR gate and an AND gate, and you do your electrical circuit. I could have used a plus, so you can just use the addition here, but still you have to do all the interface around it. And this is not the only problem, because you have a lot of engineering questions to answer when you program FPGA. Do you respect the timing? Do you respect the latching of your input signal? Because you have your input, you have to catch it at the right moment. You have to do a test bench. So basically a test bench, you have to simulate every input signal, and you will just see the output that it gives you. And you have to check if the output is the right thing that you want. So at the voltage level, I mean, it's a pretty long process. Do you have enough resources? Again, on the CPU, if you ask for a long algorithm, it's just going to take a long time to execute. Here, if you don't have enough resources, it won't fit. So a lot of questions that aren't simple to answer, and this is basically why we don't use it more, especially in audio community, because it's very specialized, and not everyone has those requirements to answer those questions. So this is what is an FPGA, basically. So you have one part of the project, and so the other part is how we make it easy for audio community to program, so using FAUST. I suppose a lot of you know what FAUST is. So it's a programming language. So it's it's a functional programming language, and it's made for sound synthesis and audio processing. Okay, so it's developed by the Graham CNCM, and it's very accessible and very used in the audio community. So that's a good start, because we want to make FPGA used by the audio community, so we use a language that is used in the audio community to program them. And something pretty interesting is that it can be translated into a lot of language, and especially for our case, in C and C++. We'll see that later. So now you should be able to understand this slide. So this is the idea behind Sifara. You use FPGA with high-level programming. So there is another problem, more than just the programming of them. I'm going to show you this example. This is some FAUST code. You don't need to understand it if you don't know how FAUST works. But the idea is that we want to do, we want to implement sine oscillation and put it inside an echo on this example. So the way that the sine is made, it's use a resonant filter. So we just need to compute the cosine value and the sine value of the frequency we want, and the filter will generate every sample of the sine. Okay, and we put it on an echo. So if you just put that entirely on an FPGA, maybe it will fit because it's a very simple function, but it will use a lot of resources. Why? First, because the echo, so an echo, if you do a 1 second echo at 48 kilohertz, you will need 48,000 samples of 24 bits. It's a lot. It won't fit on the block RAM that you have. You don't have enough memories. And the cosine and the sine function are very, very costly in FPGA resources. So how can we resolve that? Well, we don't use an FPGA in standalone. We use a CPU with the FPGA, so an ARM in this case. And the idea is that you can put every computation at the sample rate on the FPGA, and every computation which is at the control rate, you put them on the CPU. So you keep the fast computation of the FPGA, but you can dispatch some computation on the CPU. So for example, if I take the example just before, the cosine and the sine function, they need to be computed just one time. So we can do them on the CPU. And if we change the frequency, they need to be recomputed one time, but it doesn't matter if you don't do it at the next sample. You can wait 2 or 3 milliseconds. So you can do them on the CPU gives the value on the FPGA, and the FPGA do the sampling rate computation. And same thing for the memory, so we can use an external DDR, which is pretty slow, but it's very big, so you can store a lot of sample on it. And if you just need to access some sample per sample, it will be okay, because you have like a 30 access that you can do between 2 samples. So that's not a lot, but for an echo, I mean, it means that you can implement 30 echoes, so it's pretty nice. So yeah, this is the idea behind the balancing of computation. So this is what the Sifara toolchain will do for you. It's not only a FAUST to VHDL compiler. It's also, it do all the balancing. It interfaces the CPU with the FPGA, with the DDR also. It does the design choices for you. We can do that because audio program tend to have the same problematic. So you will mostly have the same amount of memory needs, of the same memory dispatching, the same resources dispatching. So you can determine what an audio program is, and you can do the role inside the compiler. And yeah, it's also there with a clocking issue, for example, which is a pretty big issue that we have. And yeah, so how can we do that? Thanks to FAUST, so I will explain that in a better way this afternoon at the workshop, but FAUST can generate two different files, and because we modified the FAUST backend. So you can have one file with all the sampling rate computation and one file with all the control rate computation. And so from that, you can execute the control rate on the ARM and the sampling rate on the FPGA. So for the ARM, it's pretty easy. It's just a C++ file. So you just have to compile it with GCC, for example, and you can execute it. For the FPGA, it's a little bit more tricky. We use the HighLevel Synthesis tools. Those are a software that is provided by the manufacturer of the FPGA. And it allows you to take C++ files and transform them to what we call an IP, an intellectual property, which is a hardware block that you can directly implement on the FPGA. So you have to tune the tools a lot, but we already do that for you, so you don't have to. And you can directly have your physical function from the FAUST program and from the CPP file, C++ file. So this is Sifara, basically. You write something in FAUST, maybe a physical model of a MooBox. You just have the command line Sifara. You have a lot of options that I will explain this afternoon during the workshop. You wait 15 to 30 minutes. It's long, but it's not very long for an FPGA. It takes a lot of time to do the synthesis and the implementation on an FPGA. Most of the time we talk about hours, maybe it's day. So here, 30 minutes, it's pretty nice, but you have to wait anyway. And you have it. You can directly flash your FPGA, and you can have the first MooBox in the world with an FPGA inside. I don't know why, but you probably want that. So yeah, this is just that. We tune everything for you. So let's say you want something maybe more interesting for music. You can control the FPGA using two solutions. You either have the GUI, which is automatically generated based on the FAUST that you write. So it's on your computer, right? And you can control the FPGA through the USB cable. You can use a MIDI controller to control this interface. So you can control your FPGA with a MIDI controller. Or you can use those open hardware board that I make. It's just 8 slots, and you can choose between a slider and a knob or anything. And you plug it directly inside the FPGA, and so you can have a physical hardware to tune your DSP. So we did a lot of work for ultra-low latency. The thing that I didn't speak about for now is that you have to have this little interface between the audio analog signal and the digital signal that you just compute. So these are called codec, audio codec. It's just an ADC and a DAC, but with a lot of filter for audio signal. And you have to use them. You cannot put some analog signal into your FPGA. The thing is, when you want low latency, this board is pretty slow. For example, our computation on the FPGA, we guarantee you that it will take only 2 samples to do any computation that you want to do, as long as it's fit on the FPGA. So we have 2 sample latency. So at 48 kilohertz, it's 40 microseconds. But the audio codec will add a lot of samples. For example, the first one we used, it was, I think, 50 samples of latency. So we try some very low latency audio codec. The lowest latency that we can find was the ADAU 1787. And thanks to that, we were able to reach the latency, the round-trip latency so analog in to analog out of 11 microseconds. So it is at 768 kilohertz. So it's allow you to do very, very low latency system. And because those codecs can be parallelized, you can have a 32 in, 32 out system at 11 microsecond latency. So it's very promising for active acoustic control, for example. So to do that, I designed this pretty big board. So it embeds a lot of audio codec, ADAU 1787. So I designed this board. You have the little chip here, which is the audio codec. You just plug 16 of them, and you have your 32 in, 32 out board, which is directly connectable on an FPGA. And you could theoretically, I didn't try for now, stack 16 of them. You have enough resources for that. And so you could probably have 512 in, 512 out system with 11 microsecond latency. So yeah, Sifara is already used in some other university. You have some example here. So it's used in Menus in Ireland, in Yale in Singapore. So it's used by the École Centrale de Lyon. You just saw the presentation this morning. And we have a collaboration with the Karma at Stanford University. We work on a WFS with them, so wavefield synthesis. And especially thanks to this future board of 32 in, 32 out, low latency audio interface. So what's next? We have some work to do. We try to embed a Linux right now. So on the CPU, you will have a small Linux that run. So you can add the Ethernet connection, for example, or a lot of interface. We try to use a FAUST to VHDL backend, which will eventually allow us to get rid of the HLS, high-level synthesis tools in the future. We have some memory accesses improvement to do. There is Florent de Dinchin, which is a pretty good researcher on mathematics that will work on the fixed point, because right now everything is in floating point. So we want to implement a fixed point version. And for now, we don't pipeline anything. We can do that. We want to work on that in the future. Yeah, thank you. So this is the QR code of the GitHub, but you have the address just here. And yeah, I have a workshop this afternoon where I will explain more technical detail about the compiler. Thank you. Question? Yeah.
So you mentioned the ARM and the Xilinx chips. So you're using, is this only working on those specific Xilinx chips that have the ARM?
Yeah, so yeah, I didn't mention that. So yeah, basically you have two big manufacturers of FPGA. You have Xilinx and Altera. For now, everything works with Xilinx. So we made it work with some Zibo boards which embed Z7, Zinc 7, and with a Genesis board that embed UltraScale Plus FPGA. So for now, we are sure that it works with that. It should be easy to make it work with other Xilinx board, but for now, it don't work with Altera product, for example. First, because we have to change every script, and also because the high-level synthesis tools are provided by Xilinx. So Altera provide the equivalent, I think, but we didn't try for now, so yeah.
What about the open source toolchain in RISC-V CPUs?
Well, we didn't try yet, but I don't think there is a high-level synthesis tool equivalent, so...
There is.
There is? Okay, so we didn't try. But yeah, we have to start with It's already a lot of work to understand how the tools work, even with something like the Xilinx, who provides a lot of documentation. So yeah, we start with those one, and we'll see after for the other one.
More questions?
Yeah.
Hi, yeah. I'm just wondering on the CPU. So you have the CPU and the FPGA.
Yeah.
On the CPU, is that running bare metal, or do you have any kind of a free an RTOS, or?
Sorry.
Is it running bare metal, or is there an RTOS on the CPU?
Right now it's running bare metal.
Okay.
But yeah, we try to put a Linux on it. But yeah, right now it's bare metal. So the CPU don't do a lot of things. It just check the input, so the ADC with the potentiometer and things like that, and it just send the value of the computation to the FPGA. So okay. Right now it's just bare metal, but we could add a lot of things on it. The thing is, we use a system on chip, so it's on the same silicon chip. You have the FPGA and you have the CPU. So it's not a CPU implemented with the resources of the FPGA. It's really you have the architecture of the CPU, so you can put a lot of things on it. It won't take the resources of the FPGA. So yeah, for now it's bare metal.
Okay.
You can say that on the CPU we do part of the init code, like
talk to the microphone because people cannot hear all
just to precise something, we divide the control code and the DSP sample level code, and on the CPU we can do a part of the initialization code is done on the CPU, and then we can share like tables for sinus kind of compilation or this kind of thing. And when we are doing a sample level thing, everything coming from the control, there is a bit of processing done on the control, like doing some computation which depends on the controller, and then we send updated values to the FPGA using the DDR transmission between the two sides, basically.
Thank you for the speech. Just you have shown a picture of your you made a board containing the analog inputs and the audio codec chips.
Yeah.
And then that board is then connected to the system on chip.
Yeah, through the FPGA, yeah, through a FMC connector, yeah.
And so you made a custom board for.
Yeah, so this one is just 3D render for now because I
okay.
I just received this one yesterday, so I have to test. This is the little chip that you want, you see on it. Yeah, because I want something modular if I want to add or more or less codec, and because the codec are the expensive part, so I don't want to solder everything on the board. So right now I just have the little board. That's that should work in the next days, I hope. And so after that, this is basically just connection. It's just you have from this little board you already have your input and output, audio input, audio output, and the digital signal. The codec handle everything, so you don't have anything to do. So you just have to connect 32 audio jack to that. This is what this big board do, but it's just wiring. It's just to avoid me to do 32 soldering on each jack.
Yeah. Then the FPGA is on a separate board or underneath.
So
or
this board is like 20 centimeter per 20 centimeter, and we have evaluation board of an FPGA with the same size. So you just stack on it, and there is a connector. There is not a lot of GPIO needs for that. It's like 20 GPIO for all the board, because every audio codec takes only 2 signals, data in, data out, and you have the 3 clocking signals that are generic for every codec. So you have 2 times 16 plus 3 GPIO, and you can time multiplex. So you can even on the same number of GPIO, you can do that 16 times. Yeah.
Yeah,
So-
I think it's really cool.
Yeah, I
Thank you.
hope it will work. For now, still in progress, but.
Are there any questions online or no? Okay, cool. So I think, well, thank you, Maxime.
Thank you.
We're gonna take a 30 minutes break. So we will resume at 11:30 sharp. We're gonna try to fix the screen issue for those of you who are watching us remotely. There is fresh coffee in the lobby and cakes and stuff like this. So yeah, feel free to grab them. And so we'll be back at 11:30. Thank you.